Hello. As Melissa says, I'm Andy Pitman. I am the director until June the 30th. I then get 1 day off, and I am then the director of the News Centre, etc., etc. So I'm going to give you 2 hours on land surface stuff. We think the land surface matters. Whole variety of reasons, most of which is it's where you get your water from, and it's where you get your food from, and it's where you get your fuel from. And whilst having your heads in the clouds or having your feet in the ocean is exciting, interesting, and everything else, actually the land is where the rubber hits the road, because you don't get crops very often grown in the ocean. So the land surface. Thanks to Mark Decker, who's sat up here in the corner for help with some of the 2 lectures. The good bits are his responsibility, the bad bits are mine, the questions are his, so you better pay attention. I'm going to cover 3 things in the first lecture. I'm going to cover the basic background of energy, water, and carbon, because if you didn't think carbon was a central part of land surface processes, you've not been paying attention. Secondly, a little bit on hierarchy of land surface modeling, how we actually parameterize this stuff in our models that we use. And then just a little tiny bit at the end on whether the models are fit for purpose, or more to the point, where our current models are fit for purpose. So, the role of the land surface. Energy, which is what you're all feeling at the moment because you're all energized. You should recognize this figure. It's the basic global flow of energy from the sun, from infrared. We're interested in 3 bits. We're interested in this bit here, which is the way the land interacts with received solar radiation and reflects some of it. If you looked in a mirror this morning, you will know that mirrors basically reflect 100% of the light that hits them. A block of coal reflects maybe 5% of the energy incident upon it. We're very interested in the difference between those sorts of concepts in the Earth system, because that affects the amount of energy available to drive other processes. We're also interested in the net infrared flux. That's the net of the incoming radiation, infrared radiation, relative to the outgoing infrared radiation. And the reason we're actually interested in these is they sum up to give us the amount of energy available to drive the 2 key fluxes I'm going to talk quite a lot about, which is the latent heat flux and the sensible heat flux. And I will talk at some length about why the balance between those 2, the way that the total energy is partitioned between those 2 fluxes, is really, really important. And it really doesn't matter too much what issues you're interested in, at least in land or atmospheric science. How the energy is partitioned between sensible and latent heat flux actually matters to you if you're interested in droughts or heat waves or deep convection in the atmosphere or the role of clouds or a whole range of other things. Here's an equation. It's a very simple equation, and you are going to find that I mix up the actual terms I use on the way through. So sometimes the shortwave flux is SWD, and sometimes it's S with an arrow. Welcome to the real world. That is how the literature works. If you can't work out that SW stands for shortwave, maybe you're in the wrong room. So we have an amount of radiation coming in, the short wave down, and the long wave down, balanced by an upward long wave flux and a reflected solar flux. That has to be balanced by 3 fluxes, basically. The sensible heat flux, the latent heat flux, and the soil heat flux. There is some other energy. Notice I'm not talking about snow, on the grounds that give another few decades you won't need to worry about it. And I'm also not worrying particularly about the energy used in photosynthesis, though I might touch on that later. That can be simplified the terms on the left-hand side of the equation sum to be the net radiation, sometimes called the available energy. The net radiation is the net amount of energy available to drive the system, to drive the land surface. And it has to be exactly balanced, thanks to conservation of energy, by the sensible latent and solid heat fluxes. So if you do something to change the net radiation, like you change the reflectivity of the surface, or you change the clouds so that there's less incoming, or sometimes more incoming infrared radiation, consequent on those changes will be a change in the sensible or latent or solid heat flux. They're all interconnected. Here's another way of looking at it, thanks to Piers Sellers, who published a really nice article on this stuff in 1997, just really showing the fluxes more simply, showing a large incoming solar flux, quite large incoming and outward going infrared fluxes, and the consequent fluxes to do with sensible and latent heat. So, let's break that down a little bit. First of all, the radiative fluxes. Depending on where you grow up, if you grow up in Australia, you might well be familiar with noontime incoming solar radiation fluxes up towards 1,000 watts per meter squared. The solar constant's 1,300 watts. It's not often you get 1,000 watts, but it's up around that order. And the reflected solar is usually 10 or 20% of that incoming flux-ish. That gives you the albedo, which is simply the ratio of the outgoing solar flux to the incoming solar flux. These are the radiative fluxes that those of you doing clouds are really, really important to. If you don't get your clouds right in your climate model, and we have personal experience of this at the moment, if you don't get your clouds right, you won't get the incoming radiative fluxes right. And if you don't get the incoming radiative fluxes right, you don't get this stuff on the left-hand side right. And if you don't get that stuff right, you won't get these fluxes right. And the basic thing in all of that is the reflectivity of the surface. I like forests. And I like forests because they're really dark. And they absorb most of the radiation falling upon them. And they therefore are active absorbers of incoming radiation. Here we have a forest. This is in the Canadian Rockies. And above the forest we get more into grasslands. And those grasslands are much more reflective. The prairies or the pastures are much more reflective than the forests down here in the valley. You'll also see this white stuff up here, snow, highly reflective and acts within the climate system very differently from any of the vegetated surfaces. We can now build on those fluxes to look at how they would be used on the right-hand side of the equation. I'm not going to talk about the ground heat flux. It's basically a conductive flux of energy into the soil. But these two really, really matter. And they are bearing on the right-hand side of this equation to help balance the terms on the left-hand side of the equation. So I'm going to talk at length about the sensible and latent heat fluxes. So here are the equations. They can be expressed in many ways. Whole papers have been written on how to express the sensible and latent heat fluxes, but this is a nice simple way. It's basically the sensible heat flux is a temperature gradient. So it's all to do with the temperature gradient, how big the temperature difference is between the surface and the air above the surface. An aerodynamic resistance, which is an efficiency term, it describes how efficiently the atmosphere can transfer turbulence away from the surface. And that contrasts with the latent heat flux, which is basically a humidity gradient. So temperature, humidity gradient, again, an efficiency term or a resistance term, and how wet the surface is. So sensible heat is about a transfer of heat in the form of energy. Latent is also a transfer of water. So, a few terms. That's what a resistance is. You should be familiar with that, I hope. These are basically aerodynamic and total evaporative resistances. These are related to how rough the surface is. So if you have a nice, smooth grassland, that is much more aerodynamically smooth than, say, a forest. Just so that you pick up the terminology annoyances, often latent heat fluxes are lambda E, lambda being the latent heat of vaporization, latent heat, or sometimes QE, depending on which terminology you use. If you come from the boundary layer micrometeorology community, you tend to use this. If you use in the climate community, you tend to use this or this. Just get used to it and be able to interchange between them. It doesn't really make much difference. It's just a terminology question. So, as I said, forests are rough. Here is a picture of a forest. It is aerodynamically rough. It sticks up into the atmosphere. The flow of the atmosphere across the surface becomes slowed down by drag. It mixes. In fact, there's eddies that form in this structure and irrigate the air otherwise trapped by the canopy. And if you don't know what I'm talking about, take a weekend off and go find a forest on a windy day and stand in it. And you will find that the wind near the surface is negligible. If you're out in the bush hiking and you're cold and wet and you want to stay a bit warmer, go stand in a forest because the wind won't be very windy in there. Whereas if you go stand out in a grassland, you'll get hypothermia and die. Here is the consequences of transforming a landscape with a chainsaw. This is Madagascar. This is aerodynamically smooth. It didn't used to be. It used to be dense forest. And in order to generate the paper that's in your photocopier, or for other purposes to do with timber, the landscape's been deforested. Aerodynamically, these two are completely different. Here, the atmosphere is being slowed down, and the air inside here is held and is transferred with the atmosphere relatively slowly, so you don't get strong gradients. At the surface here, water is evaporating up into this canopy, moistening the air within the canopy. The humidity is increasing, and therefore that moisture gradient that drives the latent heat flux becomes constrained, because the air is getting wetter and wetter and more saturated. The air isn't being mixed away into the free atmosphere, and so down here near the surface, it tends to be moist. If you go walk through that forest, you will probably find water at the surface. It's moist, lots of vegetation near the surface, lots of available water. If you go walk across this landscape, the ability of the atmosphere to suck water out of the surface and transfer it up into the free atmosphere is much more effective, and it dries out. Depending on the nature of your landscape, profoundly depends on how the net radiation is actually used. And here are two nice, simple examples, which don't take too much thinking about. If you have a lake that's wet, because most lakes on average are wet, even in climate models, you will use all your net radiation to generate latent heat or evaporation. The energy will all be used to drive a moisture flux. On the right-hand side, in your deserts, all of the energy will be used for sensible heat because there's no moisture. You can't have an evaporative flux in the absence of water. So, we get two bookends, if you like, to the entire system. A total evaporative-driven landscape and a total sensible heat-driven landscape. What do you spot as basically different between these two? What can you see? Clouds. If you're driving the system with sensible heat, and there's no moisture, you ain't going to get any clouds. If, in contrast, you're using energy to drive evaporation and you're pumping moisture into the atmosphere, you tend to get clouds, and therefore a feedback on the amount of energy available at the surface to drive processes. And these things are nicely interwoven. So, on the left-hand side, you tend to get a moist, cool, shallow boundary layer, and on the right, you tend to have a dry, hot, deep boundary layer. And that translates into feedbacks with clouds, with radiation, and all of the other really cool things that we worry about in modeling the Earth system. In order to drive latent heat from the surface, you've got to get water to the layer at which the gas exchange is taking place. And that can be in a variety of different places. But here is a good example of how forests manage to source water to evaporate. This is a non-Australian tree. You can tell it's a non-Australian tree because most of its roots are right up near here by the surface, saying that that tree isn't used to being seriously moisture stressed. It expects to get water. It expects to be able to access water most of the time, and it hasn't bothered to put roots down way, way, way deep in case of emergency where there's no water for it to transpire. Because trees die if they don't have any water. In general, though, this tree has access to lots and lots of soil where it can suck up water and happily use its net radiation to drive evaporation. In contrast to this, not a tree, this grass, if any of you have got lawns, you will know they tend to die in the Australian summer, or at least mine does. That is because the roots don't go down very deep, and the amount of soil this can access is really small compared to this. It's 10 centimetres instead of a few metres. Australian vegetation is weird. If you don't know how weird Australian vegetation is, do a little reading. It's weird at so many levels, one of which is it tends to put tap roots down to groundwater. Anyone know why? I know it's to access water, yeah, well, that's fairly obvious. Why does Australian vegetation have roots going down 10, 20, 30 metres? Oceanographers, what's your main mode of variability? And so, it appears that Australian vegetation has evolved to cope with decadal variability and drought. Northern Hemisphere variation, which doesn't experience droughts that last 10 years. Any of you ever go to England, you'll know a drought is defined by about 4 days without rainfall. Actually, it's about 2 weeks. 2 weeks, no rain, drought. The vegetation doesn't have to be adaptable to that kind of mode of variability. So in the same way as our fauna are evolved to deal with the variability driven by ENSO, our vegetation is also has evolved to cope with that mode of variability to some degree. See, land surface is really cool. I can make it relevant to ocean scientists. So here's 4 really interesting landscapes. Tropical forest. The net radiation is primarily used to drive latent heat. A nice, beautiful prairie. In spring, lots of latent heat. Later in the season, the vegetation desiccates and it tends to be more sensible heat-driven. A savanna, the trees can transpire really quite a lot through the year. The grass dies and commonly burns, and much more of a semi-arid landscape where the grasses have already died back, they're ephemeral, they come in the consequence of rain, and there's much less vegetation. Understanding the nature of these different landscapes tells you a lot about how the boundary layer will evolve over time, particularly in an event of interest. Water. This is a slide with an ocean. I'll get rid of that very quickly. This is the basic hydrological cycle. You all know it. It's taught to year 6 students, so I'm not going to dwell on it. But we're interested in the way the water is taken from the precipitation, put through the land surface, and critically, the difference between what happens to water that's held by the soil as distinct from the water that runs off. We have a nice simple equation, the basic equation that defines the hydrological cycle. Rainfall is balanced by E minus, by evaporation minus runoff minus a change in soil moisture. Again, I'm ignoring snow. This is the same as the latent heat flux, it's in different units. So the Earth's radiation balance is connected to the Earth's water balance by evaporation. Here's a nice landscape, a nice semi-arid landscape with a few interesting terms. Rainfall must be balanced by evaporation from the soil, actually from moisture being vaporized at the skin of the soil and put into the atmosphere. By transpiration, that's water that comes from inside a leaf to outside a leaf. Water that's been intercepted by a leaf and evaporates. If you don't know what that is, go stand under a tree in a rainstorm and discover that you stay dry because the leaves are very good at capturing the precipitation. Don't do it in a lightning storm because trees are also good conductors of lightning. Surface runoff, that's water flowing over the surface. Runoff draining down into the soil and any change in soil moisture. Go back to the picture of a tree with its roots. Water flowing across this surface. Here's a picture of water flowing across a surface. It's called surface runoff. Water that drains down into the soil column and then laterally flows is usually called drainage, and it ends up in rivers. This stuff ends up in rivers too. Surface runoff, water flowing across the surface, is actually quite rare. If you've gone hiking and seen surface runoff, you were already soaked before you saw it. It's quite rare. It's actually quite rare for water to pond and then flow across the surface. Okay? It's much more common for water to flow into the soil, laterally through the soil, and come out in the form of rivers. Here's a slide from Mark, which just builds up the various components of the water balance. You have rainfall. It's difficult to think about moisture in the land surface without starting with rainfall. Interception. Water's captured by leaves very effectively. Throughfall is the water that is intercepted that then drips to the surface. Infiltration is the water that flows into the soil. Overland flow or surface runoff is the water that's unable to infiltrate and flows horizontally across the surface. It matters what the soil is. If you have a lovely, rich, dark, organic, loamy soil, this stuff hardly ever happens. If you have a really horrid clay-rich soil, it might be more common. So the nature of the soil, the structure of the soil matters. Saturated zone, which is mostly the area of the soil above the groundwater. Water being redistributed in the soil down to a water table. The water table is the beginning of the saturated zone, which is deeper in the soil. And whilst most northern hemisphere vegetation, this is apparently a tree, your cartography skills, no, not cartography, drawing skills need a little work on tree. This is an interesting tree that comes from where Mark lived in North America. Tends to put its roots fairly shallow. The Australian vegetation commonly puts its roots right down into the water table. Groundwater recharge, subsurface flow, all being basic terms in the hydrological cycle. Land surface models, because if we're talking about climate and future climate, it comes back often to modeling, resolves many of these processes. And in fact, Mark has been working on parameterizing groundwater in the sorts of climate models we use for climate projections. this is actually complex, getting all these things right. And the hydrological cycle is at least as difficult to capture in our models as the energy cycle. Third, carbon. You'd be fairly familiar with this, and because you'd be fairly familiar with it, I won't dwell on it. We are mainly interested in the carbon that's being managed in the atmosphere land system over here on the left of the picture. Getting rid of the ocean as quickly as I can, we can focus in on the overall terrestrial carbon balance. Again, because it's really hard in a climate model to simulate coyotes and foxes, we'll skip the animals out of this as quickly as possible and focus in on the role of the land surface in managing carbon. Carbon is absolutely critical to understanding how a land surface operates within the climate system. And it's all down to these things, stomates. If you go and get a leaf and rip it off of a tree and look at it through a microscope, you will see that there's really tiny pores populating the surface and sometimes the underside of a leaf. And those pores are the most single important component of the Earth system. Possibly not quite, but I'm going to argue just for a minute they are the most important thing. And if you don't know what they are, then you've obviously not been studying hard enough. Stomates take energy, photosynthetically active radiation from the sun, and they use it to fix CO2 from the atmosphere and consequently release oxygen and water vapor through these pores on the leaf. So, in the circumstances where there's energy, to get the CO2 into where the energy is performing photosynthesis, these pores have to allow carbon dioxide in and consequently necessarily allow water vapor out. The water vapor flux is called transpiration. Stomates are, I think, and I might be wrong, but I think they're the only place in the entire Earth system where energy, water, and carbon are coupled and occur simultaneously. Now, there may be a couple of other places, for instance, phytoplankton in the ocean, but we're ignoring those for the time being because we're talking about the land. So, these things, stomates on the surface of leaves, are really important. And an awful lot of the questions and issues about how the climate system will evolve in the future comes back to the change in the net carbon balance and how that net carbon balance influences the water and energy balance, or how a change in the water balance affects the carbon balance, or how the energy balance changes affects the water and carbon balance. They're all intertwined, and I'm going to talk about that in a minute. One of the fundamental laws, you know about conservation of energy, you know conservation of mass, but there's also basically conservation of carbon. If something enables trees to take up more CO2, they have to do something with it. They might say, I've been struggling a little bit with drought, and I'm going to deal with this little extra payment I have on carbon. I've been able to take up a bit more carbon. I'm going to use and allocate that carbon, and I'm going to use and allocate that carbon to grow deeper roots. As an evolutionary strategy to beat my competitors, I'm going to put my roots down a bit deeper so I can cope with the next El Nino that comes along better than that other tree next to me. And it will use its carbon to allocate more root growth. If you have more roots, longer roots, you can access more water, you become more drought tolerant, and you tend to, in the future, use more of your net radiation towards latent heat over sensible heat. So there's a feedback here, both in terms of evolutional adaptation and in terms of the ability to access water and continue to evaporate longer into a season because you've used that extra money you've got, or carbon, to grow more roots. But you don't have to do that. You might want to grow bigger or more leaves. If you've got more carbon, you can invest it. How do I decide whether I should invest it in roots, or should I grow taller, or should I grow more leaves, or should I grow bigger leaves? And one of our big challenges in modelling land surface processes is working out what a tree will do, or what our vegetation will do. Will it grow more roots to become more drought tolerant? Or will it grow more leaves, which adds to the vulnerability that the vegetation would have to drought? So it matters one hell of a lot for you doing rainfall modelling or cloud modelling. We need the seasonal variability in the rainfall sorted, please. Because if we don't have the variability in the rainfall, the adaptive strategies of the vegetation to changes in rainfall won't be done right. No pressure. So, those are the basic concepts in land surface modelling that we've been working on for a very long time. And they go back in climate modelling to Manabe, who was one of the people who built the original climate models, GFDR model, and included in the GFDR model a very simple land surface scheme called the bucket hydrology parameterization, which was 15 centimeters deep everywhere. It generated no drainage. You only got runoff when the bucket was full and then overflowed. It ignored carbon and was still being used in the second assessment report by the Intergovernmental Panel on Climate Change, which was, I think, 1995. So, there are still climate models you can find, very rarely now, that use this very simple global fixed water holding capacity in the soil with very simple parameters, with a very simple partitioning between latent and sensible heat. If you go back to papers by Manabe and Weatherall and others, you will find lots of early papers, including some in Nature, which showed one of the key projections from future climate simulations being mid-continental drying. This turned out to be because this land surface scheme didn't parameterize seasonal water storage very well. It dried out much too quick, got much too dry, and therefore we got these projections of future climate at continental scales showing much too much continental drying. This is known as a first generation land surface scheme, and if you are using a climate model with one of these, stop it. It is provided for historical purposes only. Our second generation models were instigated by a guy called Dierdorf. He left science to chase UFOs, I kid you not, which is a bit depressing because I don't think he produced very many papers, but they're all amazingly impressive pieces of work. The Dierdorf scheme, which evolved into a number of land surface schemes that are still used, doesn't traditionally do carbon. It was common in the second and third IPCC reports, and it's still basically how some land surface schemes are parameterized in climate models. There is a really critical error or feature in this model, and that is it does not explicitly couple energy, water, and carbon. It couples energy and water in a stomate, but it's not biologically informed. So it doesn't fully couple the three key terms. And so we moved to a third generation land surface scheme, which is common in IPCC reports 4 and 5. It's still used. It does carbon. It also formally couples energy, water, and carbon in ways that plant ecophysiologists broadly accept as basically not completely stupid. And there's lots of different ways of parameterizing this little bit, and they're improving, and I won't go through the detail of those because an hour of photosynthesis tends to tax the audience. But these third generation schemes are now pretty much state of the art and formally couple energy, water and carbon. So something that the stomate does here on the canopy affects energy and water, something that affects energy also affects carbon, etc., etc. An important thing about these two schemes, the second generation, which were common up into the 2000s, and the third generation, which are newer, everything else can be the same. How you parameterize soils, how you do everything else can be the same. The difference is how stomates are treated, and the big advance in these newer schemes is the formal coupling of energy, water and carbon in an ecologically or biologically reasonable way. And those of you who haven't caught up with the news that Graham Farquhar at ANU won the Kyoto Prize a couple of days ago, which is the Nobel Prize for proper science. He got that by being the person who understood or substantially understood how stomates work, which is really cool. Once you've got your land surface scheme behaving itself and working properly, you can do stuff. But I'm working vertically down here from an atmospheric model coupled to a land surface model, coupled to how vegetation phenology, that's leaves and stems, are updated as a function of the CO2. This tends to be parameterized in our new third generation models. And then there's a whole new, completely separate science called DGVMs, Dynamic Global Vegetation Models. These are the things that allow vegetation to migrate across the landscape on paleo timescales. So if you're interested in paleo timescales and you're interested in paleo timescales and carbon and vegetation dynamics, you need one of these. If you're interested in how weather and climate will change over the next 30 years, you probably don't. But how you pick your land surface scheme fit for purpose is actually quite challenging. So that brings me to the question of fit for purpose. We have a hierarchy of land surface schemes. They range from the sublime, which is the, sorry, that's got that round the wrong way. They range from the wonderfully sublime models which we're currently using, which are perfect in every way, aren't they, Ned? Through to the ridiculous, in hindsight, which is the Manabe scheme, which has been demonstrated to have a range of systematic errors. I am going to assert, for those of you who aren't working in land surface modeling, that if what you're actually excited by are these sorts of pictures, on the left is the global simulation of temperature. This is something that some of you will recognize by Multi-Meinhausen, which is looking at the probability of whether the planet will avoid 2 degrees of warming for a given range of emission scenarios. I suspect the sorts of second or third generation land models we're using now are fit for purpose. So if you're interested in the large scale, or you're interested in ocean dynamics, or you're interested in global scale averages, or even continental scale averages, and you don't care about carbon, these second or third generation schemes are probably fine for you. If, however, you're interested in stuff that's responding to the land surface, things like droughts or heat waves, or carbon balance, or continental water balance, or the impact of double CO2 on human health, if you saw the paper that came out in Nature today, those sorts of things, you've got to be very, very careful that the land surface schemes that you use are evaluated for your purposes, work for the purposes for which you tend to implement them, and you make sure that they are actually resolving the processes that you think matter to you. So, some conclusions from the first 50 minutes. I talked about the role of the land surface in energy, water and carbon. And I tried to get across a simple message. that it's only in the more recent land surface schemes, the so-called third-generation land surface schemes, that energy, water, and carbon are properly coupled in a physically and, most important, biologically consistent way. If you're interested in those sorts of things, carbon balance, response of vegetation to double CO2, evolution of landscapes under climate change, changing landscape vulnerability to drought or heat waves, those sorts of things, you need to be careful with the land surface scheme you're using and make sure it properly couples energy, water, and carbon. I discussed the hierarchy of land surface schemes, taking you through 40 years of history in 3 slides. It's only the third generation schemes that are biologically informed. The earlier schemes were not, and you need to be careful if you're using them, and some older climate models still use them. You've got to be careful if you're using them that you don't then use results from the land surface if those results would otherwise be substantially affected by how you do the land surface. And then I then talked about fit for purpose. If you are worrying about the detail of how the land is evolving, or you're worrying about the detail how the land carbon sinks are changing over time, or you're interested in phenomena like droughts and heat waves, be careful. Be very careful that the land surface schemes you're using in your models are fit for purpose. And the rest comes after a well-deserved coffee break. But I'll take some questions if anyone has any, except from Ned, who asks difficult questions.
So you're basically saying at the end there that the second and third generation land surface models are fine as long as you're not actually looking at land? Or are there some land problems for which they are still fine?
You need to do a careful evaluation of that case by case. So so you need to do that case by case. Right. As far as I'm concerned, if you're actually looking at a system that responds to CO2, you need to make sure that your land surface schemes can deal with the impact of that CO2 on the energy, water, and carbon cycles in a coupled way. So yes, there would be land surface problems that I'm sure we could think of where you get away without worrying about that full coupling. I'm struggling to think of any off the top of my head. But you do need to carefully evaluate the models fit for purpose. Not what we all do, which is go to the literature, find a paper that says this model works really well, and use it, and then cite that paper as evidence that you've carefully evaluated the modeling system you're using. Yeah?
Some of these land surface processes like drought and intraseasonal variability or seasonal variability that you mentioned that land surface being important for may actually have an upscale impact on the larger scale climate. So I feel like there's a bit of a missing link between saying the models are okay for looking at some of that large scale stuff where there might be problems in the small scale variability when there's that interscale link.
Yeah, that's a fair point. Except to get that link right, you've got to have the land surface tendencies to the boundary layer scheme right, and the way the boundary layer scheme then is interwoven with the free atmosphere. So that's more than a land surface problem. I'm kind of reflecting on what you need to get the tendencies right. But yes, if you want to simulate drought properly in a climate model, it then comes back to the timescales that you're trying to simulate drought. If you're trying to do interdecadal transitions of a landscape to drought, you need a different land surface scheme than if you're simulating seasonal drought, where the vegetation doesn't respond to that. But yes, I've been arguing for many, many years that if you're an atmospheric scientist interested in large-scale phenomenon, you cannot just assume the land surface is a static, non-changing, simple sponge that provides some fluxes. You've actually got to make sure that the land surface scheme captures those processes which feed into your problem. And there has been some really nice work done in the last few years, mainly out of Europe, which is showing how influential the evolution of the land surface is to specific phenomena like heat waves. I will talk about that after a coffee break.
In the formula for latent heat, I think they use the temperature of...
Sorry, say that again slowly.
In the formula you chose for the latent heat fluxes.
Yeah.
I think so. The temperature that was used for the saturation water vapor was the temperature of the surface. Why isn't it the temperature of the air?
You calculate the specific humidity of the two things, but you can assume that the surface layer is saturated to that temperature.
I have to think about that.
No problem. But you do calculate it in the atmosphere to the temperature of the atmosphere.
Temperature of the atmosphere.
The reference height above the atmosphere. So you're calculating a humidity gradient between an area above the soil and the soil surface itself, or the vegetation surface itself, depending on where that flux is transferring from. So you calculate the flux from the soil to the atmosphere separately from the water interception of the leaf into the atmosphere, separately from the water inside the leaf through the stomate into the atmosphere. So you calculate all those things separately, and then you aggregate them depending on the geometry of your land surface scale.
So it seems a little bit different from saying that you just look at the moisture difference.
I was simplifying it. Because Mark had about 30 slides, breaking those things down step by step, and I figured I wanted to get out of here alive.